In these notes, we're going to talk about what you've been doing in the light bulb lab. So we're going to summarize what you should have learned in that lab, and then we're going to go ahead and talk about power and introduce a couple of new ideas as well. So let's get started. You have been measuring current. And in an ideal world, we would have given you some of these notes before you started with the lab, but we had some AP testing going on and we weren't able to do that, okay? So let's define a few things that you've been doing. So current, and we're going to use capital I. Some people use little I. I usually use capital I. Is going to stand for electric current. And it's simply the rate at which charge passes a point. So current is equal to charge over time. So if we were to look at units for that, we know our units that we're using for charge are coulombs. And we know our standard units for time is seconds. So the units for current are coulombs per second, but you used something else in the lab. You used amps. So it turns out that a coulomb per second, we have a special name for that, and it's simply called an amp. And most people use capital A to stand for amp, okay? So current is simply the flow of charge past a point in a given amount of time, okay? The next topic we're going to talk about is a little more difficult, and I'll put it in quotations because I don't really like that term, but I do use it, okay? So voltage is an electric potential difference. And it's measured across an electric component. So a light bulb or a battery or something like that, okay? So voltage is equal to a change in energy divided by charge. Now, the hard part with voltage is, well, why don't we just measure the change in energy? Why don't we just look at the change in energy without having to divide out the charge? The problem there is, and you don't have to take this in your notes, it's just a little aside, because I'm not an electrical person, I'm a mechanical engineer by education, so voltage always confused me. But the way I make it simple is I turn it into a mechanical problem. And I say, here is the ground, and I have an object, a mass, and I'm going to move the mass from one height to another. And we remember potential energy, gravitational potential energy, to be mgh. And if I were to look at this, I might say, well, that's a pretty decent distance that it moved, so I'm going to say that potential energy changed by quite a bit. I'm going to say that's a large change in potential energy. But then along comes something else, right? And it's a much bigger mass, and it's moved from there, say, to there. And I look at that, and the center is moved significantly less than in the first object, the much less massive object. But from that distance to the next distance, that's still a very large change in gravitational potential energy because there's such a big mass. But if all I really care about is what is the difference in energy from one location to the other, I really want to take the mass out of the equation. I want to get rid of that mass. I don't really care about it. I just want to know, well, what's the change in potential from one location to the other? That's what voltage is, okay? So voltage is simply a measure of the change in energy from one location in the circuit to the next, but you're taking out the effect of having a large charge versus a smaller charge traveling, okay? So that's just a little aside. Don't worry if that wasn't super helpful for you, okay? So we're going to measure voltage just like you did in class. Our units are going to be volts. But take a look at what a volt is. A volt is simply change in energy, so it must be a joule divided by, well, if it's divided by charge, it must be a joule divided by a coulomb. So you might see those units as well, but in general, we're just going to use volts, okay? The next thing that I'm going to talk about is resistance, and resistance is something we didn't talk about in the lab, okay? All electrical components have resistance, so resistance is simply a measure, and it's a little bit of a circular definition here that I'm going to give you, so I apologize. So it's a measure of a material's resistance to current, or to the flow of charge. Now we're going to measure this in these units you're probably not familiar with. We're going to measure this in ohms, so our units are going to be ohms. And one would think that, oh, we're going to shorten that. I can, just like with amps, I use A, or with volts, I use V. We can use O for ohms, but you can't, because if you were to write 1 and then an O, it would look like a 10. So instead of using an O, we use an omega, which looks like an O with a couple of feet. Okay, it's called omega. It's simply another Greek letter. It's a capital Greek letter. Okay, so not too big of a deal there. Now, and I'm not gonna go too deep into this because you guys just want the results. We're gonna talk about Ohm's law. So Ohm got a unit named after him, and he's got his own very own law. And Ohm's law states that in a circuit, any component, the voltage over that component is going to equal the current through it times the resistance of the object. So voltage is equal to current times resistance. So we can always calculate an object's resistance if we measure the voltage and the voltage across that component, the current through it. We can always calculate the resistance. Okay. So we're going to use this, and we're going to keep that in mind because that's going to help us think about a couple of things. So now let's get to where we were looking at the lab, okay? And let's take a look at a series circuit first, and let's see what you saw, and we'll talk about what you saw in the lab. So a series of circuit looks like this. We've got a battery. This is usually the plus side. This is the minus side of the battery. And we connect that up, and we've got a light bulb, and then we've got another light bulb. And we can label a couple things. So this battery has some voltage, and we're going to call that V, the battery. And then we can measure some voltage across light bulb 1. We'll call that V1. And we can measure some voltage across our second light bulb and call that V2. We also know we've got current, so we can measure the current from the battery, and we would just call that I of the battery. And then we can measure the current through light bulb 1. We call that I1, and we can measure the current through light bulb 2. And then, of course, we also know that this light bulb must have some resistance. We'll call that R1, and we'll call the resistance of the second light bulb R2. So you should have seen a couple of interesting things in your lab. The first thing you should have seen, and let's talk about the current. So if current is the flow of charge, it's just the flow of electrons. We'll talk about it, we consider it the flow of a positive charge. We'll get to that in a little bit, okay? So we've got some electrons flowing, okay? And they can't leave this wire. They can't just poof, jump out of the wire, right? So they're stuck in the wire. So whatever charge is being delivered by the battery has to also flow through this first light bulb, and also has to flow through the second light bulb and then be returned to the battery to complete our circuit. So you should have seen in your lab that the current from the battery is equal to the current through the first light bulb, which is equal to the current through the second light bulb. That has to be the case, okay? So that was the first thing you should have seen. The second thing you should have seen has to do with the voltage, okay? Now remember, voltage is basically an energy drop dividing out the charge. So let's say that the battery can deliver 3 joules of energy per coulomb. Okay, so 3 volts. So that's 3 joules of energy are being delivered. Well, the whole job of the light bulb is to convert that electrical potential energy into light energy. So if we deliver 3 joules of energy to this light bulb, and it uses 1 joule of that energy per coulomb to convert it to light, we've still got 2 joules of energy left. So this light bulb has to use up those 2 joules because we have to end up back at the battery without any energy. Any energy that's delivered has to be used up in the circuit, okay? So you should have seen then that the battery voltage is equal to the voltage drop across resistor 1 plus the voltage drop across resistor 2, okay? So that's what you should have seen. Now the last thing, the resistance, I'm just going to give this to you without much proof. And we're going to talk about the equivalent resistance of the circuit. Because the battery is dumb. The battery doesn't know how many components are connected, nor does it care. It just knows it's connected to some resistance, and it's going to deliver current based on that. So we call that the equivalent resistance. that the battery sees. It has no idea how many light bulbs, it just knows that there's something connected to it. So we can calculate the equivalent resistance, which is basically what we would replace all this stuff with if we just wanted to have one resistor. So for a series circuit, our equivalent resistance is just going to be the sum of any resistors that are connected to it. Okay, very straightforward. All right, let's go ahead now and let's talk about a parallel circuit. So let's go ahead, let's draw our parallel circuit. So this is hopefully what you created. Okay, you had a battery, and then you had one complete circuit with your light bulb. And then you wanted to add another light bulb, but you didn't break the circuit. You wanted to add it in parallel so that there would be another path for the circuit and the current to flow. Again, we've got some battery voltage, and we can measure the voltage across this first light bulb and call it V1. We can measure the voltage across this light bulb and call it V2. We know we're going to have current from the battery. We know we're going to have current through this first light bulb. We know we're going to have current through this second light bulb. And we know that this first light bulb is going to have some resistance R1, and the second light bulb will have some resistance R2. So let's talk about the current now and how that's going to work. So again, we've got current coming from the battery. Okay, so the battery is the source of all of our current. Okay, so we have the current coming through here. It's going through this wire, and then it gets to this junction right here. Now the current has a choice. Just like when you are driving in your car and you get to a fork in the road. You can either go to the right of the fork or you can go to the left of the fork, just like the current here. So some of the current's going to go through this this light bulb, and some of the current's going to go through this light bulb. But if I have 5 amps of current and 2 amps go through this light bulb, that means 3 amps have to go this way. The current can't jump out. I can't get any extra current, right? So we've got to maintain, kind of conserve current here, okay? So what you should have seen then is that the current from the battery is equal to the current through resistor 1 plus the current through resistor 2. The voltage, on the other hand, is going to be a little bit different. The voltage is going to be the energy loss per coulomb when we travel in a circle. So some of the current is going to go like this. We're going to start out, let's say we have a 3-volt battery. So we're going to start out with 3 joules of energy. The current's going to go through this light bulb, and it's got to end back up at 0 here. So we have to take those 3 joules of energy. This light bulb has to use up all that energy so that when the current gets back here, it's at 0 joules of energy per coulomb. Same thing's going to go here, right? We've got 3 joules of energy. Some of the current is going to go this way because that current is carrying the energy. So this light bulb has to use up all 3 of those joules. So what you should have seen then is that the voltage from the battery is equal to the voltage over resistor 1, which is also equal to the voltage over resistor 2. The resistance, the equivalent resistance that the battery sees is going to be different than the equivalent resistance in the series circuit. So if we go back and we look at the series circuit, we should see that when let me get my little pointer there. So we should see that if we were to add another light bulb here, the resistance in the circuit would increase, okay? That's the opposite of what happens in a parallel circuit. So in a parallel circuit, if we were to add another resistor over here in parallel, we would see that now not is there only one way and 2 ways for the current to flow, there's a 3rd way. So that's like adding lanes on an interstate, right? If you've got one lane on the interstate from here to downtown Chicago, it's going to get really packed and the resistance is going to be really large. But when you add in a second lane, you're decreasing that resistance. And when you add in a 3rd lane, you're decreasing that resistance. So the equivalent resistance, the equation for the equivalent resistance is kind of tough. So it's 1 over the equivalent resistance is equal to 1 over one resistor plus 1 over the second resistor, okay? So now let's talk about a couple of other things, all right? So when I add a resistor in series with the battery, okay, the resistance increases, and then let's remember our Ohm's law, okay? So our resistance in this in this circuit is going to increase, okay? Our voltage hasn't changed. All of our voltage is still coming from the battery. So if we increase that resistance and we don't change the voltage from the battery, we know our current is going to go down. Well, you saw that when you took one light bulb in series with another light bulb. You should have seen that the current went down, and the way you noticed that is because this light bulb became much dimmer, right? These two light bulbs in series were much dimmer than just one light bulb, okay? Likewise, when we look at our parallel circuit, when we added a second light bulb here, our resistance went down. I can tell because this light bulb didn't dim. It didn't dim at all. So we must have gotten more current from the battery. So the current increased. The total resistance went down, but the total current went up. The voltage of the battery didn't change. So the last thing we're going to talk about now is we're going to talk about power. I don't know how that happened there. There we go. So we're going to talk about power. We've talked about power before when remember we did the horsepower lab when you guys ran up the stairs? So power is just a change in energy over time, okay? And if we look at that, we know we're going to end up with joules per second. So where do we have joules in our equation, in our electrical circuit components? Well, we know that voltage is a measure of power per coulomb. So we know that power is going to be voltage times, well, even if I just look at the units here, I've got joules per second that I want to end up with, and voltage, remember, is joules per coulomb. So I better multiply that by coulombs over seconds in order to get power. Well, what do we measure in coulombs per seconds? We measure current in coulombs per seconds. So power is just voltage times current. But remember, we have a second equation here that V is equal to I times R. So I could also rearrange this power equation, VI, and I could place out that V with IR, and I would see power is also I squared times R. Or I could replace that I, because I see over here I is just equal to V over R. Power is also equal to V squared over R. So I can use these equations when I'm comparing the power used by different components. Because, for instance, if I know, say that I've got a circuit set up and that I've got two components and they each have the same voltage, but one has more current, I'm going to know that that component with more current is going to be using more power. Okay. Similarly, if I know that two components have the same resistance, but one has more voltage over it, I'm going to see that power is greater. Okay. All right, I think that's about 17 and a half minutes of notes. That's more than anybody can take. So I'm going to stop there. I'm going to encourage you to try the Mastering Physics, and then if you have questions, let myself or Mr. Welter know. Thanks, guys.